Good morning. So we'll continue with the lectures on enclosure fires. We were talking about the in and outflow of gases from enclosure and what happens during fully developed stage. So let us consider the enclosure which has a opening of height h0 and the gases within the compartment are at a uniform temperature of Tg and its density is rho g, and the mass flow rate of the gases out of the compartment is m dot g, and its velocity at the exit of this enclosure is Vg, the average velocity. Then we have some mass flow rate of air coming into the compartment, which is m dot a. Now you can see that out of the opening height h0, there is a layer which is called neutral plane, which actually separates the incoming and outgoing flows. Above the neutral plane, the hot gases goes out, and below the neutral plane, there is the movement of air inside the compartment, into the compartment. So how to find the mass flow rates? For that, let us consider. So let us first take the outgoing gases. Consider 3 points along the ocean above the neutral plane, that is 1 within the enclosure, 2 well outside the enclosure in the ambient, and 3 at the exit of the enclosure. The fully developed stage, the hot gases rise up and the smoke flows out from the top portion, and the cold airflow comes into the compartment through the lower part. So this is separated by a virtual plane which is called neutral plane. The flow is triggered due to pressure differences, again due to temperature differences. Basically, in the top portion, the pressure inside the compartment will be more than that of the ambient, so that the flow goes out. In the bottom portion of the compartment, that is below the neutral plane, the ambient pressure will be more than the compartment pressure, so that the air comes in. This actually naturally sets up. The pressure difference is naturally set up. So at the neutral plane, the pressure difference is 0 because the flow is reversing the direction, and the height of the neutral plane is Hn, as denoted in this. From the bottom or the floor, the height at which this flow reversal happens or the pressure difference becomes 0 is, that is inside and outside compartment, the pressure difference is 0. That is occurring at a neutral plane located at a height of Hn from the floor. Now let us obtain the mass flow rate out of the compartment, considering the 3 points as I mentioned earlier. Point 1 well within the enclosure, point 2 outside the enclosure in the ambient region, and point 3 the exit plane of the enclosure where the flow goes out. So we will apply the Bernoulli equation. This is a simplified analysis. So we apply the Bernoulli equation. Pressure, say at the point 1, pressure is P, so P1 by rho g. So I am just multiplying by rho. So P1 plus Vg square at point 1 by 2 into rho g plus Gzu into rho g. If you go back, you can see that here the height, total height of the opening is h0, Zu or Zu is the height in the top portion where the flow goes out, and this is above the neutral plane. Similarly, below the neutral plane, h0 minus Zu will be Zl, that will be the neutral plane height also, and here the flow comes in. Now what is the Bernoulli equation is applied to the top portion here. So at the point 1 and point 2 or point 3, you can see that the Zu is used, G into Zu is used basically. So that's what we are using here. So Zu rho g G. So rho g, why it is used? Because at the point 1, hot gases are there. Hot gases are present. So rho 1 will be equal to rho g. So that's what we have put rho g here. Okay. Now in the point 2, which is well outside the compartment or enclosure, pressure is P2. Okay, atmospheric pressure. P1 is the pressure inside the compartment, P1. P2 is the atmospheric pressure. Now, please see that the density of the air, atmospheric air is used here. Velocity of the atmospheric air divided by 2 into, again, rho A is used here. Rho A Zu into G. So, this is the Bernoulli equation applied at the point 1 and 2. 1 is well within the enclosure, 2 is well outside the enclosure. Now, we can see that the flow goes out. Basically, what happens is the pressure difference here will be such that the pressure will be uniform for some time, then it decreases only at the exit plane. Okay, the pressure is uniform like this and it decreases at the plane and goes to a lower pressure. So here, so that means we can see that the flow is induced only at the exit basically. So considering the velocities, here the velocity it will be stagnation. So it will be the velocity is approximately 0 here. Similarly at the point 2 also velocity will be approximately 0. Only at the point 3 you will have a velocity, so Vg at point 3 will be positive because it is going in the inside to the outside. Okay. So now if you see that, apply this here. So velocity is point 1 and 2 well inside the enclosure or well outside the enclosure. The velocity tends to 0. Okay, as I told you, the pressure actually remains constant. This is exit plane. Only the exit plane it decreases and becomes again constant. So here and here there is no pressure gradient to drive the velocity. Only where the pressure decreases the velocity is generated. So here point 1, this is say point 3 and this is point 2. Point 1 and point 2, the pressure gradient is almost asymptotic. So the velocity will tend to 0. So we can say that both Vg1 at point 1 or Va at point 2 both are 0. So the second term drops. So we can say the pressure difference between point 1 and point 2, P1 minus P2 will be equal to, I can say, delta P in the upper zone, that is above the neutral plane. Above, that is delta P above the neutral plane. That will be equal to G Zu into rho G minus, rho A minus rho G. Okay, G Zu into rho A minus rho G. That will be the pressure difference. So now you can see this pressure difference is positive because rho G is hot gas density which is lower than the ambient density. So this is the positive term. So this is the pressure difference in the upper zone, which is P1 inside the enclosure, P2 outside the enclosure. That is positive. That is the maximum pressure difference in the upper part which drives the flow. The expression, simple Bernoulli equation is used. Now let us take the point 3 here and point 1 and apply the Bernoulli equation. Point 1, the same equation, P1 rho G Vg1 by 2, but this is 0 because we have discussed that, and Zu rho G G equal to P3 here at this point, P3. So you can see that the P1 reduces to P2 through passing through P3. So P3 will be in between P1 and P2. Rho G Vg 3 square. This will be the velocity of the gas which is flowing out as a average velocity you can take at the point 3 plus rho G Zu into G. Now again this is 0. So P1, this P3 take the other side. This is the pressure difference exactly at the just before and after the exit plane, or before the exit plane and the exit plane. P1 minus P3 equal to rho G Vg 3 square by 2. That means Vg3 or the velocity, this is actually average velocity of outgoing gases, let us say, that will be under root 2 P1 minus P3 by rho G, or now P1 by minus P3 can be written as this, no, Z U G into delta rho. Delta rho is rho A minus rho G by rho G. So this is the expression. So this will be the maximum velocity you can say, or average velocity. because they are considering maximum pressure difference. No, so that is what. So now we can also say that P1 minus P3 will be approximately equal to P1 minus P2. Again, we can, this is the pressure drop, but any pressure drop actually causes the flow. Since we are trying to take some average value, we can say that this difference and this difference will be the same. Now, let us do the same analysis for the mass flow into the compartment. Now, what I do is I go to the figure here. I consider 3 points again below the neutral plane. One is 0.4, which is well within the compartment, 0.6 well outside the compartment, and 0.5, which is the at the exit plane of the compartment. Here, apply the Bernoulli equation considering 2 points at a time. Let us say 0.4, which is inside the enclosure, and 0.6, which is outside the enclosure. And 0.4 and 6, the Bernoulli is applied. 0.6, which is outside the enclosure, P6 is the pressure, rho A is the density of the air, which is outside the enclosure, velocity VA6 square divided by 2 plus, because now we are in the below the neutral plane. So, rho A ZL is the term used here into G equal to, within the compartment pressure is P4 plus rho G Vg 4 square by 2 plus rho G ZL G. That is the equation. Now, please see that as we argued before, well outside the compartment this tends to 0, well inside the compartment the velocity tends to 0. Now, neutral plane. So, this is upper portion. So, this is ZU. So, neutral plane, this is the floor, this is ZL. Now, neutral plane is taken as 0. So, now this is negative, this is positive. So, we can see because Z equal to 0 starts here, Z is negative below the neutral plane, Z is positive above the neutral plane. So, we can say that P4 minus P6 equal to delta P in the lower zone or below the neutral plane equal to GZL into rho A minus rho G. Now, please see this, ZL is actually measured from the top. Now, Z direction is actually, if we say Z direction is positively upward. Now, since the origin is now shifted to neutral plane, this is negative. So, this P4 is what? Pressure inside the enclosure is pressure outside the enclosure. That is negative now. That means P6 is greater than P4, the flow comes in. So, maximum negative pressure difference in the lower part of the vent. Now, take the cases. So, this is the lower part, 0.4, 0.6 and 0.5 here. So, now apply the Bernoulli equation between 6 and 5, because I know the flow is now coming in this direction. Previously, I took 1 and 2, correct? 1 and 3. Now, I am taking 6 and 5. P6 outside the compartment, rho A, the density of the air there, VA6 actually is going to tend to 0, and here rho A G ZL. Here P5 at the exit P5. So, this is the plane. So, this is in compartment, this is the exit plane. P5 is the exactly pressure at the exit plane into VA5. The air is coming in this direction now. So, you understand? Air is coming in. So, the velocity of the air entering the compartment into ZL rho A G. So, this is the expression I get here. Okay. Now, P6 minus P5. P6 is the point here outside. This minus P5. This is positive, correct? So, that will be equal to rho A VA square, VA5 square. That is the velocity of the air at the exit plane coming in, equal to VA5, implies VA5 equal to 2 into P6 minus P5 by rho A. Now, I can put modulus of ZL here. because ZL is negative, but in the square root I put modulus. Anyway, I want the magnitude of this velocity, correct? Magnitude of velocity coming in will be equal to 2 ZL G rho A minus rho G. Always rho A minus rho G is positive by rho A. So now P6 minus P5, P6 minus P4 equal to the pressure difference, and VFI is the maximum or average incoming velocity. So now from this I got two expressions. The velocity at any, so now we have seen maximum velocity and average velocity I have found, correct? See what is maximum velocity? If the velocity profile is say non-uniform or parabolic, I can say that will be the maximum velocity what I get from the maximum pressure difference. If I have a uniform velocity, then that will be the average velocity also. So now let us say Z is the direction. So this is the neutral plane where I put Z equal to 0. Positive direction is the upper part where the flow goes out. Negative is the lower part of the neutral plane where the flow comes in. Now I can say that the velocity of the gas as a function of Z above the neutral plane can be written as 2ZG rho A minus rho G by rho G under root. This is outgoing velocity. So now you can see, you put Z equal to 0, obviously Vg will be 0. When you increase the Vg, this Z, then Vg increases. Similarly here, Va is the incoming air velocity. So at again Z equal to 0, it will be 0 at the neutral plane, then it increases when you come down, okay. So here also you can see that Va at any Z equal to under root 2 Z. I put modulus because Z is negative actually below this, so modulus. So magnitude I have to use. So magnitude of the velocity I am finding. So 2 ZG rho A minus rho G divided by rho A. Okay. Now this can be integrated over the entire thing, and we can find the velocities. Okay. So this is the velocity of the outgoing gas, incoming gas by simple Bernoulli equation. Please understand that we are not taken into account of viscous effects etc. here when you do Bernoulli equation. So that means, see, due to viscous effects, when there is a solid wall, the velocity there will be 0 or the velocity of the wall itself. That is called no slip condition. That is due to viscous effects. But here, when I use Bernoulli etc., I don't consider viscous effects. It is a simplified thing. So what I can say is, I can try to find the maximum velocity, average velocity, or some variation in the velocity below and above the neutral plane. Now let us find the mass flow rates of the outgoing gases. How to find this? See, for any vent, see, let it be orifice or any slot or anything, any vent, where before and after the vent there is a change in area. Okay, what happens in the enclosure? There is a vent. Okay, and before the vent you can see that there is an enclosure. Maybe in this case the enclosure height and the vent height are the same. But outside the vent you can see there is a sudden increase in the area. It can go freely to the atmosphere. So if there is any area change before the or in the exit plane, okay, before or after the exit plane, then we will have what is called some coefficient of discharge. Also this coefficient of discharge comes to take into account of the viscous effects. So mass flow rate of the gases outside the going out of the enclosure can be some coefficient of discharge into, I integrate the mass flow rate from the neutral plane. Z equal to 0 is neutral plane, Z equal to Zu is the top part of the neutral plane. Density of the, I am considering uniform density of the gases. Velocity, I have expression, correct? For this velocity I have expression which is shown here, this expression here. Okay, now use that and into dA. Again area we can find. Area is what? The perpendicular area through which the mass goes out. So that I can do like this. So here you can see that W is the width in the perpendicular direction, that into dz, that will give the area. So this integration I do. So here W is the width of the opening and all of the properties of the enclosure are assumed to be constant. So that means rho, g, t, g, etc. are constant. So that's called well mixed scenario. That is enough. Okay, anyway, because of the eddies, etc., the smoke layer, there will be lot of convective mixing. So there is nothing wrong in taking a well mixed scenario for the gases inside. Similarly, when it goes to atmosphere also, soon it reaches the atmosphere conditions. So there is no problem. So as I told you earlier, the Z is defined as 0 at the neutral plane, and outflow occurs from Z equal 0 to Z equal to ZU. So now I plug in the equation for Vg as a function of Z here, and W is constant, CD also I know, by experience only I will know that, rho g also is taken as constant. So just integrate this, I get a expression, equation A, which is the mass flow rate of the gases going out of the enclosure, which is some coefficient of discharge, width of the vent, the density, the average density, let us say, of the hot gases into under root 2g rho a minus rho g divided by rho g into 2 by 3 Zu power 3 by 2. That is the average or steady mass flow rate. The actually fully developed condition is a steady flow rate also. That is the outgoing mass. Equation A gives this. So this means one thing is unknown. Out Zu is itself is unknown here. That means if the neutral plane is not, if neutral plane height is not known to me, Zu cannot be found, correct? The neutral plane is the origin now for us. So here you have to get some expression for neutral plane, then only Zu can be got. Now what is the mass flow rate of the atmospheric air into the enclosure from the region below the neutral plane? Okay, that is again calculated in a similar manner. That is the coefficient of discharge, there is a area variation, and also there is some viscous effects. So there is a coefficient of discharge, integral 0 to ZL, okay, rho a Va Z dA. So now integral rho a is constant, Va is Z into W into dZ, same thing what we have done. Now Z is defined as 0 at the neutral plane and inflow occurs from Z equal to 0 to Z equal to ZL. Now plug in the expression what we have got for Va here, this expression, so that I can get the expression for the mass flow rate of the air coming into the compartment. They are exactly the same procedure. The only thing is here I am trying to take the magnitude of Z because it is negative, no. So CD W rho A integral of 0 to ZL under root 2Z G rho A minus rho G by rho A dZ. So when I integrate this, everything is constant. See, rho G is taken as constant because we are saying well mixed scenario. Rho A obviously is constant, and integral 0 to ZL Z dG. So I get same expression, but instead of this Zu, I put ZL here. So ZL is also not known till Hn is evaluated. Obviously Hn will be equal to ZL. Okay. This is the rate of mass flow rate, steady mass flow rate of the incoming air into the compartment under fully developed fire. This we should not forget. These two expressions are steady state where fully developed fire is occurring. So you know that once the flash fire occurs, for a long duration steady burning will occur. That steady burning is called fully developed fire regime. There these flow rates are applicable. Now we know that the total ventilation height is Zu plus Zl, H naught is Zu plus Zl. Okay. Under steady conditions, in the steady fire, when the fire is burning in a steady state, steady condition prevail, then the mass flow rate of the gas inside, coming inside, will be outgoing mass. Or else what happens? The neutral plane itself will change, correct? If the outgoing mass increases, incoming mass reduces, etc., the neutral plane itself will try to change its position. So let us consider a steady fire, that is lot of commodity is set to burn. So we are having a steady heat release rate. That means the burning fire is also steady. The steady state outgoing mass and incoming mass are there. Neutral plane is also at a particular position. It is not changing its position. Under this condition, the incoming mass should be equal to the rate of the outgoing mass. So let us equate these two. Incoming mass equal to outgoing mass. When I do this, see, probably the CD value need not be same for both the cases, but let us assume that to be same or in the same range, say 0.8 to 0.9, something like that. So that I equate these two. When I do that, I get this expression where rho A by under root rho A, ZL power 3 by 2 equal to rho G by under root rho A, Zu power, so it's actually under root G, Zu power 3 by 2. So now I can find the ratio of Zu by ZL power 3 by 2 equal to rho A by rho G power 1 by 3. That's it. So now, since this ratio is known, then there are two expressions now. I know Zu by ZL from this expression. Now I know H naught equal to Zu plus ZL. So from this I can find ZL, which is equal to Hn. That's it. Okay. So you will see that the neutral plane location, if it is got, then the mass flow rates can be found. See here, vent opening is known to me. Rho A and rho G also are known to me, steady fire. So ZL can be got. Once ZL is got, which is Hn, I can find Zu, and once I get Zu and ZL, I can find the steady state flow rate for incoming and outgoing masses. Anyway, CD has to be determined using the experimental value. It may be within, say, in the range of say 0.8, 0.9, so on.